right, this is a fantastic honor to be here. This is certainly going to be my first time that I'm going to be drinking and presenting at the same time. It's never done this. At home when I drink a beer, I'll fall asleep right after that, so I'm not sure how coherent I'm going to be at the second half of this. But anyway, I'm going to talk about living with AI. This is a translation of the Dutch, which reads a lot better. Overleven met kunstmatige intelligentie. So I'm going to talk to you a little bit about the Turing Test, a little bit of an introduction, and then I'm going to talk about societal challenges, the ones that you just saw on the image in the preview, and then a summary. And by the way, that's a computer algorithm that is combining flowers and dogs. It's called GenBreeder. You can do this online if you like. It's sort of art produced by machine learning. All right, so let's start. In 1943 or around that time, Alan Turing, who is the godfather of sort of computer science, you can think, he developed what we call now the Turing Test. And a Turing test, as we read here, is a test for intelligence in a computer requiring that a human being should be unable to distinguish the machine from another human being by using the replies to questions put to both. So, in an image, that is basically that image there, a person is behind a laptop trying to answer, sort of actually ask questions to somebody behind a wall. Behind the wall could be either a AI or a human. And if the person there doesn't figure out whether he or she is talking to an AI or to a human being, then the AI actually has passed the Turing test. In fact, this is a shifting boundary because we now have systems that almost pass the Turing test, and then of course people say, no, this is not what I mean more like this, and it becomes more and more difficult. But what I really like is sort of this movie. So in the movie Her, basically what you see is the first sort of Turing test in action, if you want, and I think this will probably be the first truly intelligent system that we will interact with. So don't think in terms of robots that are dangerous or that are, talking to you or something like that. It is much more like what we were going to see now in this little fragment. So this is the movie Her, and he has just started a new operating system.
How would you describe your relationship with your mother?
It was fine, I think. Well, actually, I think the thing I always found frustrating about my mom is, if I tell her something that's going on in my life, her reaction is usually about her. It's not about...
Thank you. Please wait as your individualized operating system is initiated.
So he just bought a new operating system, and it's
Hello, I'm here.
Oh. Hi.
Hi. How you doing?
I'm well. How's everything with you?
Pretty good, actually. It's really nice to meet you.
Yeah, it's nice to meet you too.
right. So that is basically, I think, the first time that we will be talking to an AI. This is the typical way that we will have a conversation with an AI, not a robot, but more like a system that lives in your computer or in a cloud or something like that. And if you think this is very far into the future, Google recently introduced their Google Duplex, which is a system that can actually phone up a restaurant and make a reservation.
So how can I help you?
Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd.
So this is the
Sure,
AI.
give me 1 second.
It's the human
Mm-hmm.
AI.
Sure, what time are you looking for around?
At 12 p.m.
We do not have a 12 p.m. available. The closest we have to that is a 1:15.
Do you have anything between 10 a.m. and 12 p.m.?
Depending on what service she would like. What service is she looking for?
Just a women's haircut for now.
Okay, we have a 10 o'clock.
10 a.m. is fine.
Okay, what's her first name?
The first name is Lisa.
Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd.
Okay, great. Thanks.
Great. Have a great day. Bye.
So in fact, the system was so good that the person, so that in fact people called Google and said that they should identify whether the person is talking to a computer or to a human. So it's so scary good that you can really not figure out whether that's a human or a robot you're talking to. Not only because things are pronounced very well, there's also things like and the kinds of stops in there, but also the system adapts to the things that are being said by the person. So this is already pretty far. Of course, it's in a very narrow domain, right? It's not a very general domain, but anyway, you can sort of extrapolate from that, and you can see that you can pretty quickly get to something that we saw in the movie Her. Okay, so that's the introduction. Now I'm going to give you a little bit of a technical introduction. It's not really technical, no equations, but I'm going to give you a little bit of an introduction to AI and the technology behind it. So in fact, the real reason why we are seeing the current sort of revolution, if you want, or explosion, is what we call Moore's law, which is exponential growth in computer power, which already happens since the 70s. So every about 18 months or so, the amount of compute power doubles. And it's really, this is an exponential growth law, every 18 months twice as large. And it's quite amazing that this is already happening for so long. And it's still not quite finished, although some people have predicted the end of it. I think it will still be going for a little bit. So then, more recently, another exponential growth sort of law happened, which is the law of big data. Again, around 18 months or so, 2 years, the amount of data in the world doubles. We are now at about 5 zettabyte, and a zettabyte is a 1 with 21 zeros behind it. So it's a really, really large number. This is the amount of bytes that we generate currently in the world. And of course, all that data is being used by models. So here we see a deep learning model, which is, I will talk to you a little bit more about what that is. But it's one of these models that are being very successful, for instance, in the Google Duplex system that we just saw in sort of answering questions and producing speech. And you can sort of think as the compute power as sort of the engine. And you can think of the data as the gasoline that powers it all, and then the models are sort of the car. Okay, so what is AI? It's actually a very broad set of things. It's not just one thing, but if you have to, characterize it in a single sentence, I would say it is the art of making machines smart, or the science of making machines smart. And there's many ways you can do that, but let's look a little bit at the different subfields that are within AI. So, of course, we all know robotics, right? So, factories are filled with robots that make sort of cars all fully automatically. And then, of course, in the future, we all hope that we're going to get the self-driving car, which is a smart, a robot in itself. And then we just heard something about speech generation. So that Google system that we heard speak, that had to generate sort of a kind of speech which is a lot better what we heard from the sort of Hawkins speech generator, which sounded very robotic. But nowadays, and this is actually quite recent, we can generate speech which is indistinguishable from human speech. As well as language technology. And language technology is not just producing speech, it's also understanding sort of the words that come into a system and making sense of it. And so if you can think, for instance, in automatic translation. So this is a system by Microsoft. It's Skype. It's Skype has been bought by Microsoft, and they have a system where you can speak in English, and then it will automatically translate here in Spanish and reverse. Right. So this is real-time sort of speech understanding. So you first have to understand the speech, then translate it, and then in this case they write it out. But then you can also then produce it again. So fairly soon you can just have earplugs in and somebody can speak to you in Spanish, it gets automatically translated into another language, and you can speak back in your own language, and then this other person will again get it translated in their language. So the language barriers, I think, will pretty quickly disappear. Another thing is image and video analysis. So there we see a street scene, for instance, seen by a self-driving car. There the system has completely analyzed that image. It has segmented out all the different objects like trees and cars and road and and buildings and such, and it has classified them into the right class, right? And it can also identify actions like driving or walking or things like that. And so this system can already sort of recognize in the order of a couple of thousand objects fully automatically, and it can do it at this point almost as good as a human being. There we have search and recommender systems. So it is something that people not immediately think about when they think about AI, but it is the thing that they interact with most, in fact, that is AI, which is search. Every time you're behind Google and you type something into Google, you get a response that is actually there's a fairly complicated algorithm behind it that will produce for you the right search results, and these are personalized because the system learns who you are and what you're interested in, and what day it is, and all these kinds of things factor into that. And recommender systems are things like Netflix. If you want to figure out what is the next movie that you want to look, then Netflix is the recommender that produces ranks the movies and puts it in your face, the ones that it thinks you are most interested in. And then finally, expert systems, and I don't know if you have followed this, but that's, for instance, Watson, IBM Watson, who won this television game called Jeopardy. And so it had to, again, understand what people were saying. It had to then search into a huge database and figure out what the right answer is and then produce the right answer. Actually, it should produce the question in this case, which is a bit of a funny game. But anyway, it is an expert system that analyzes a lot of data. Okay, so that's a little bit of an overview of all the different types of AI that people are are researching. And then there's also sort of a hammer, like you learn mathematics in school, and with mathematics you can do all sorts of other things, right? You can use mathematics in basically all the exact sciences. So also in AI there is a big hammer, and the big hammer is called a neural network or machine learning. And the hammer tends to find nails. So the nails are, the image analysis and the language understanding and all these things. And what we've now recently seen is that when you hit those nails with the deep learning or the neural network hammer, then things start to work a lot better than they did before. So let me say a few words about a neural network. So here we see what happens in a neural net. So neural networks are a lot bigger than this image. So we now build neural networks with billions of actually for these connections that are here between, and with millions of those nodes. And each one of those nodes is really something like a neuron in your brain that can get activated and excited. So we give it some information at the input, let's say an image of some dog or a cat, and then, in the beginning these are just pixels, and then we have detectors for edges, and then we have detectors for dog noses, etc. And then at the very end there is a node that just tells you whether it's a dog or a cat. And then you have classified, that image and and you can sort of predict that there's a cat or a dog in that particular image. Now these types of models have been, used a lot to, to analyze or to deal with a lot of these AI problems. And I'll talk more about how that works in more general terms. So you can think of machine learning basically as a self-programming software. So in the old days, or what we are used to thinking of traditional software, which you see there, which is just a whole bunch of lines which say things like if, I'm in front of a red light, hit the brake, or if the light goes green, you can hit the gas, right? So these millions and millions of these lines. In fact, a car has about 100 million of these sort of rules in software encoded, but they're very static. They don't change, right? This is it. Once you have that line of code, you have to do a software update to improve your car. Now, a self-programming software, a self-learning system, you can think of as, well, the language, the computer language is not these kind of pieces of code. Well, that's behind this as well, but it's more like, a neural network with connections that, that interact with each other. And The thing is, as data flows through the system, it can actually update itself fully automatically. So it can start learning from its mistakes and say, well, that was clearly wrong because, maybe, you hit a tree or something like that, or, whatever happens that was clearly wrong. And then that information flows back into the system, and these connections are being adapted and changed so that next time you're doing better. And that's called, backpropagation. It's a type of learning algorithm, that we use. So you can think of it as differentiable programming. Maybe it's a technical term, but it's like there is a computer program, but you can update the program by taking gradients. I don't know if you still remember what this is from high school, but that's you can change that program, or it changes itself basically. So maybe at an abstract level, if that was too technical, I think at an abstract level, the best way to understand what machine learning is to think of this as follows. So the data that comes in is in the form of, let's say, an image, or many images, in fact. And for a computer, an image is just a big bag of pixels, right? It's not like when we look at that, we see all sorts of things, but that's because we are trained to see these things, right? But a computer just sees a huge amount of pixels. Sort of, it sees this, right? It's like not actually some structure. And then what it does is it applies a sieve. And the sieve says, well, all the useless information goes in a big garbage can, because I need to sieve out all the stuff that I don't need to make predictions or to understand the world. And there's only a small piece of that data that goes into, the model, which is sitting down there. And then once you have all that sort of useful information encoded into the parameters of your model, basically, then you can use that model to make new predictions. But you have removed all the garbage, basically. So let's do a little experiment. Who does not know what this is, in the sense of what to do with it, maybe? Is there anybody in this room who has no idea what this thing is? Is there anybody in this room who has ever seen this particular chair? Because I guess we all know it now. Right? Nobody has seen this chair, right? And so that's kind of amazing, actually, that you know what this is, but still it's something that's very, very different from any chair you've ever seen. Moreover, it's two-dimensional. It's not even a three-dimensional thing. You're seeing an image. You're seeing nothing else, a bunch of pixels. And yet you understand that that's a chair, and if you see one in real, you can sit in it. Okay, so how is that possible? We call that process generalization. Right? We can generalize from a bunch of chairs to whole different chairs. And that's really what's amazing about learning, and especially about humans. They can do this very, very well. And there is humans actually also that cannot do this. And for them, every time they see something new, which is that chair, for instance, they have no idea what it is. Right? Everything is always new to them. So they remember everything, but they never generalize a concept to a new object. And that's, it's very hard to understand the world if you have that. Okay, so let's see how that works with the sieve. So, what did you do in your brain? You took the complicated pixels image, and you threw away basically everything. And then the only thing you sort of left with this very abstract concept of what that chair was, which is basically maybe 4 lines. You can sit in it, there's something in your back, and you can sit in it. So you can basically encode that with, 4 lines if you want, right? And that's what's in your model. And so the irony of it all is really to know is really to forget, right? You need to know what to forget. And of course, not forget everything, but you have to forget 99% of what you see. And figuring out what to forget is really the art of learning and also the art of generalization. Okay, so then there is 3 categories of machine learning. So I'm still talking about that big hammer that we hit sort of all these problems with. And so there's these 3 different types of ways that we can learn. So the supervised learning is the way, if we think of the analogy of children, is that your mother is sitting next to you, you're trying to figure out maths, and your mother tells you, you have to do this if you add things and do this when you subtract things. So there's supervision, when you're trying to learn things. But that's actually a very small part of human learning. The bigger part of human learning is unsupervised. And unsupervised learning is I just look into the world and I'm trying to make sense of it. I see repeated patterns. I see people do things, right? I see, and I'm going to extract concepts and abstractions out of that sort of complicated world. And that process is called unsupervised learning. There's nobody holding my hand to figure out, to tell me how the world works. I just have to figure it out by watching it. And then the third one is actually, the real sort of more overarching framework, which is called reinforcement learning. And in reinforcement learning, you do experiments in the world. So in these two, it was all passive. But this one, you can actually start doing things. You can invent, you can make your own hypothesis. You can think, well, okay, I think if I throw this into the room, right, what will happen? That's an experiment I can do, right? And then, if I don't know what to do, then, I will figure it out by throwing. And then I've learned something in the world, right? And so that's called reinforcement learning. And the big difference is that here, you actually, you can act on the world, and you can change the world around you. And that's quite different. And robotics is squarely in this field here. Okay, then unfortunately this one is not can't see very well, but let me give you a few examples of supervised learning so you get a sense of what we do when we do supervised learning. So the top one, so I've actually worked on myself. You get a three-dimensional MRI image from your brain, and you pump it through your neural net, so that's a particular kind of neural net. And then you have in your data set, you have like 1,000 of these MRI images, but you also have 1,000 of these labels, because you know that in 5 years this person actually developed Alzheimer, or this person stayed healthy, right? And so you have these labels, and then you're going to train that network there to basically find subtle patterns there in that MRI scan that are indicative of that prediction. And a human does this by looking at the hippocampus. And if the hippocampus is small, it means that memory is impacted negatively, and it means that there's a higher chance of getting Alzheimer. But there's many, many more super subtle patterns in there. Where like maybe if the brain region on the left is a little bit more active and the one on the right is a little bit smaller, and in addition to the some stuff in the back of the brain being slightly different, those are patterns that humans really can't see. Certainly not in three-dimensional images, but computers can see, and so they are actually better than humans in this. The other one was a paper in 2017. So you see there a skin lesion. It's a melanoma. And then, so there was a method that was trained on 130,000 images, photos of skin lesions. It was pushed through the network. And again, it had to recognize up to 700 classes of skin lesions. And here they did a test where they compared that system to Stanford doctors who were wide awake and knowing that they were competing with this sort of algorithm, and of course they didn't want to lose, and they were very good sort of dermatologists. And so the blue line is the computer, because it can sort of operate in any possible operating configuration, and humans are the red dots, right? And there's this one person here that sort of seems to beat at that particular operating point the computer. But all the other dermatologists sort of were worse than this system. And the lesson we learned from this is that on a very well-defined, narrowly defined problem, like melanoma detection, and if we have enough data, in this case 130,000 images, which is actually not a lot if you think about it, right? There's far more images in hospitals. Then we are starting to surpass human precision. And this happens only once, right? So it's kind of nice that that we are seeing this in 2017. From this point on, humans will never catch up, right? Because these systems will get smarter a lot faster than humans can catch up. And then here's a third one. And there should be sound, but okay. Yeah, there we go. So what we see is, again, an image, and it gets segmented out and classified real time. So this is a Microsoft system. Right, so that's now basically state of the art. You can take a video and real time analyze everything that's in that image, segment it out, and sort of classify it. Okay, so these are all examples of supervised learning. Now let's look at unsupervised learning. So this is a system that gets fed, couple of thousand images of faces. These are celebrity faces, so they're all beautiful people. And then it basically said, okay, just watch this. and try to understand what's going on, right? That's all the system had to do. But then once it was done, then they asked, okay, now you generate new faces, right? Since you understand the space of faces, now you just generate new faces. And so what you're going to see is you're going to see the system generate faces of people that don't exist. And if you look well, you see that this particular person will turn male and female back and forth, right? It's kind of amazing. So this system had to go through this sort of this particular phase. Okay, it's still training, right? It's 4 days training, 5 days training, 6 days training. But now it's basically done and it's generating things. And you can see, someone, and you see a guy, and then you see now you see like a woman, right? And so these faces are amazingly accurate. I mean, I would not be able to see the difference. And there's actually a website now, like Person or Not or something like that, where you are asked to distinguish between these two. So you're doing a kind of a Turing test with this particular face generator, and you can hardly tell the difference. Okay, and then the final one is reinforcement learning. So in reinforcement learning, as I said, it has to do with robotics. So this is a system that is trying to do something. And this is the really important task of flipping a pancake. Of course, it's really important that we solve this problem. And here you're going to see how that works. So first somebody tells it, okay, this is how you do that, And its sensors now feel, okay, how do I do such a thing? And then there's a phase where it's going to try itself. And every time it tries something, it learns, right? It learns, oh, this was wrong. Okay, and now we'll have a little bit more. So this is after 20 trials now. Hoppa. And now the system gets improved, and it has learned to flip. And again, once it knows how to flip, it will never forget. And every system, wherever it is, we could be in Australia, it can instantaneously flip pancakes as well. Okay, and if maybe you've seen this in the news or not, but this particular type of algorithm, this reinforcement learning algorithm, was used recently, or in 2016, to sort of beat the best human player in the game of Go, which is that you have to put these stones on the table. It looks simple, but it's a horrifically complicated game. And experts were very, very sure that an algorithm would not be able to beat the best human in like 20 years, right? But in fact, the system did beat it 4-1. It was a huge hit in Asia. And now the system has already been improved quite a bit more, so it can now train basically in 4 hours a new system that will beat everything you've seen before. So these are really, really powerful systems. Okay, so that was the first part. How am I doing on time? And this was the point where I was getting a cocktail, I think, but anyway. And so this is sort of the technical part. And then the second part, then we're going to talk more about societal challenges. So of course, all of this is very nice, but everybody is very, very worried about all of these things. And that often happens because new technologies are typically scary, and this is no different than other technologies that are being introduced. We're going to look at a few of these challenges that all of this new technology poses to society. So the first challenge is actually causality. And many of the systems that are being made actually don't make a difference between causality and what we call correlation. So they are very good at detecting correlations between things, which is if this happens, then that tends to happen as well. But they're not very good at figuring out that this is actually causing that. And that is a very different thing, as I will try to argue in a minute. And it turns out you really need causality for decision making. If you don't know what causes what, it gets very hard to say, well, let's change this, because if this is not actually causing that, and you're changing that, you're not changing anything, right? You're not changing the thing that you actually want to change. So you really need to figure out that, yes, this actually causes this, so if I change this in this way, then it will have that effect, right? So let's have a look at this particular example. So the example is, and this is a real, by the way, right? So this is a real, this has really happened. So they collected data on basically a pneumonia, and they checked whether people had pneumonia, whether they had asthma, and whether they, died or whether they survived, right? And then, so they figured, of course, out that pneumonia has a negative effect on survival, right? If you get pneumonia, oh, look at that. Thank you so much. That looks very exotic, right? Okay. Let me continue with the talk. So the pneumonia has a negative effect on survival, clearly, right? But they found something really amazing, which was that asthma had a positive effect on survival, right? And then, this was in the data, right? So the data said that asthma had a positive effect on survival. And of course, you can now try to say, okay, that's great, right? We are never going to treat people for asthma again if they have pneumonia because they'll survive better. So that would be a policy, right? You could say that's what we want because it falls out of the data. But the problem is that they didn't figure out what the real sort of causal structure of this was. And here's the real causal structure. Pneumonia and asthma have a negative effect on survival, obviously. However, asthma and pneumonia caused the doctors to prescribe more antibiotics, and that was not in the data set. And of course, the antibiotics had a positive effect on survival, more than the negative effect of the asthma, right? So if you were treating much more aggressively with antibiotics if you had asthma, which improved your sort of chances of survival. So this, I want us, and there's many of these other really interesting sort of stories like this. In fact, in Schwab's book on the brain, he has this example where during birth, if you have a very difficult labor, then there is a higher probability of having a child which has a mental disability. And you would think that the difficult labor was the cause of the disability, but it turned out that in many cases it was the opposite. So the mental disability of the baby was actually the cause of the difficult labor. And the reason is that the brain of the mother and the brain of the child have to really collaborate to actually, get born. So that's also very surprising. And if you don't think hard about these things, then in fact, you can make terrible mistakes, and also you make the wrong decisions. Okay, so then let me try this for a second. Oh, it's amazing. Thank you. Okay, so the second challenge I want to talk about is recommender systems. Now, we already use recommender systems every day, right? In particular, these kinds of navigational systems. I mean, at least I use it every day to get from A to B, right? But there's also, in Amazon, when you buy something, you'll get all these other things that the system wants you to sell because it thinks that you're going to be interested in that. That's a recommender too. Spotify, recommends you new songs, and Netflix recommends you new movies, and you can even get recommended, a new mate, right? A new husband, or and there's a recommender behind that too, because that basically figures out precisely how you work, what your profile is, what you like, and then it will sort of recommend you a new love. Now, we can ask many questions about this, right? So one question could be, will we trust these recommenders at some point more than we will trust ourselves, right? And so this is an interesting question, because in the beginning, when I was using those navigational systems, I thought, I know better than a system, right? And so if it said something really weird, I said, no, that's wrong. I'm just going to do my thing, right? And of course, yes, I would end up in a big traffic jam. And then at some point I said, okay, so apparently the system knows traffic better than I do, and I'm going to follow it, right? And I predict that this will happen with all of these systems. You'll maybe resist a little bit, then you'll figure out that your life actually gets better if you follow it, and then you start to follow all of these recommendations. in fact, you could argue that those people who will be successful in life, will be the people who are actually using those recommenders most effectively, because they get, or a company that has a recommender that recommends the right policy for a company might be the most successful company that survives. And so we might just get into this, without actually knowing it. We just might get into a world where we basically follow constantly what recommendations we get. And then there's interesting questions we can ask about that, right? What does it do to our psyche? Do we start to feel like a robot? If no decision, we don't have to make any decision anymore. Right? Every decision is being, talked into our ears. It's just, we don't have to do any decisions anymore. We don't have any free will. Maybe the sense of free will will even go away, because basically we feel like a robot. Whatever we do is something that's recommended to us. I have no idea, but that's, something that could happen. Okay, another piece of, another challenge I would say is augmented reality. And so, we all know that boys are basically, gaming all the time, and girls are doing social networks all the time, right? So they're constantly behind screens. And so apparently this is extremely addicting, right? So that's what I'm sort of deriving from this. So this will get more and more true, right? So these systems will get more and more realistic. They will be more and more attractive to us. And in fact, they will also be more and more in our face, right? Because, what if, we have glasses and basically the information and the virtual world is directly projected onto our glasses. All the information is right there. I could enhance the world around me, like here, right? I could just figure out, how a system works. I can open it up, but I could also paint the walls in the color that I like. I can, change the world around me. And in fact, I can completely disappear in a virtual world where everything is better than in the real world, right? And so it is actually very addictive, and it is a battle for our attention. So these systems battle for our attention. And you can ask again, what will that do to us, right? Will we still invest in the real world? Like I think in The Matrix, if you've seen that movie, right? If we might stop investing in the real world and just live in the virtual world. Will the virtual world and the real world start to blur? If you constantly live in half real and half virtual world, maybe it's harder to figure out what's real and what's not. Maybe you were just projected here, right? Or half of you were projected here and it was completely real to me. I don't know who's real and who's not real in a world where that is completely, hard, impossible to figure out. So the next challenge is obvious, right? That's privacy. And I think this is maybe one of the biggest challenges that we are facing. Many people may not realize it, but their phones will actually track every movement you make. So in fact, I at some point was in a shoe store. I had my phone with me, but I wasn't on my phone or anything. It was just, trying on shoes. And then I came home, and then for the next 3 days on my Facebook, I only got sort of advertisements for shoes. And I thought that, that cannot be, chance. And so I started to look a little bit into this. And basically what's happening is that your phone tracks precisely where you are, and it figures out that you're in a shoe store, right? And that gets, Facebook gets notices this, and they'll start, giving you these advertisements. So it basically means that, your phone knows where you are, but, the vibrations in your phone can also figure out what you're doing, if you're in a car, if you're walking. And I don't think we know half of what's being produced and being sort of sold to companies. And of course, when you extend that to a smart city, where the whole city is being censored, and you can't say anything without a sensor hearing what you're saying, we have to ask ourselves, do we really want that? And at least we should ask ourselves the question, how can we protect ourselves from that data falling into in the wrong hands, right? And so we should really think hard about, okay, yeah, AI is going to give us really great sort of new opportunities that we should follow, but we should also be very careful with who owns the data and what is going to happen with the data. And there is solutions to this, right? It's not that there is no solutions to this, but it's something that that's regulation that has to be made and politicians have to act on. So a place where all of those this information is being sort of generated is what we call the Internet of Things. So here you see an image of all the machines that we have in buildings, in our homes, but also carry on our bodies. All of these things will actually generate data, and that data will be uploaded to the cloud. So can we keep that data in the hands, out of the wrong hands? And the other thing is that can we come up with sort of AI solutions or machine learning protocols that can still train interesting models on that data, but that guarantee the privacy of the people who produced and generated that data? And the answer is yes, but it has to be implemented. Okay, profiling. So we all know that we've seen these things typically in the news right here. Typhoon, which is a rapper, has been sort of arrested or searched, basically because he was driving in a very expensive car, and apparently it was because he was just a rapper which had a lot of money and he liked big cars, right? And so we made the wrong inference about that. And this is racial profiling clearly. There is an actual application here that predicts whether somebody is a terrorist from a single image of that person, which is totally impossible. But anyway, there are actually agencies using that particular tool, which is very dangerous, clearly. And this one was in the news more recently, which is, some researchers figured out that you can predict homosexuality from a single image, which I think there is some truth to that, but you may want to ask whether something like that we want to operate, on. If it falls in the wrong hands, clearly, very bad things can happen. So we have to really think hard about when we make these algorithms, what are the implications of those algorithms? In China, they now have a social credit rating system, which means that the data of people is being collected, it is being stored, and it's being used to increase or decrease your social credit. So if you do the right thing, if you don't walk the red light, then you get social credits. If you do the wrong thing, you get less credits. And by the way, your friends also get less credits. And so, and then if you have a lot of credits, you can take a first-class ticket by the train, or you can have an extra child, or good things. And if you have not enough credits, then of course you're being punished. So let's look at fake media. Clearly, can we all know that we have a lot of these what's called fake fake news. Deep fakes is a particular algorithm that can swap faces, right? And it's totally realistic. And so the question is whether you can actually maintain a democracy if you have this type of systems where people will believe the things that they see, and you can produce a lot of misinformation. And I think we have seen the results of that recently in the United States. And then, of course, the question about the wealth inequality and the wealth inequality and the unemployment. Will AI actually increase the inequality gap, or will it not increase that? Will we maybe produce more jobs or less jobs with AI? I don't think many people know it. I would predict, at least in the sort of somewhat longer term, we will actually produce a lot of new jobs with AI. There's a lot of new opportunities. In the very, very long run, I don't know what that means. If everything is being done better by algorithms, I think we may want to start, getting a good hobby or something like that. But I think that might, that in the long run, I don't know. Okay, so what is important is that we actually will generate trust in AI, right? And so we need systems that can explain themselves when they make predictions, right? If we get a system that says, you have lung cancer, then that should not be the end, right? Then we should either visualize that to the doctor, or we should have a conversation with such a system. So this is a more sort of a nicer type of interaction you have with the system, which says, what type of bird is this? And then it says it's a cardinal because it's a red bird, red beak, and a black face. You can also ask, why is it not a flycatcher? And you get some answer like, it's not a flycatcher because it does not have black wings, right? So you can have a conversation sort of with your AI system so that it can explain why it took a particular decision alongside nice visualizations of the decision. Okay, then the final topic is AI and creativity. So so you can ask the fundamental question, can an AI actually become creative, right? Or is it only humans that can be creative? And in my opinion, I think there's nothing mysterious about creativity. It's combining a lot of information, new information, information into new concepts. And we are seeing small baby steps in that direction. So here's a particular, piece of maybe not real art, but it's funny, it's interesting. So we have an image there, and then we get sort of a particular painting, and then we repaint the particular photo in the style of that painter, right? And so here is the Munch, and so here we have sort of the photo repainted in Munch style. So a bit larger. Here you see Van Gogh. It's the picture being repainted in Van Gogh style, and here's exactly the same picture painted in Munch style. And you can see the screamer still, right? If you see it, it's like in the corner there. So it really wants to put the screamer somewhere, and then it's right there. Okay, so we started with a Turing test, so we're going to end with a Turing test. So I'm going to ask you to point out which one is made by a human and which one is actually made by a computer. And so you have to raise your hand. So the rule is you have to raise your hand either here or there. So you cannot never raise your hand. So so you can think about, so one of the two is a human, one is a computer. So we're going to raise your hand. Who thinks this is made by a human? That's basically everybody. And so the other people think that that's a computer. Let's see how well you passed the Turing test. Okay, so great. You're doing great. Next one. Who thinks that is made by a human? Who thinks this is made by a human? Okay, that's the big majority thinks that's made by a human, and that's a computer. I got you there. Pretty difficult. So then here's another one, which is so this is a system that was trained on all of Shakespeare, and you're gonna have to figure out what is Shakespeare and who's not. So this one is "Thou art a very earth," and the other one, "Mine eyes smell onions." Okay, who thinks that is Shakespeare? And who thinks this is Shakespeare? Oh, people don't know actually. So I think some people are not raising their hands now. That's Shakespeare. This is like you're crying, right? This. All right, here's another one. Last one. Not last one. Dost thou thirst, base Trojan, to have me fold up Parsa's fatal web? Or if my true Amen is full of gold, I shall be pearled. Good. Shakespeare? Shakespeare? I think most people figured it out. Okay. Okay, so then last thing is about superintelligence, because that's the big question, and science fiction is full of it, right? Everybody worries that we will grow a super intelligent robot that will then exterminate us, much like the Terminator, the exterminator. But here's my my counter question, which is, yes, philosophically, this is not impossible in 100 years, right? And so the question is, do we have to worry about that now? Because maybe we can worry about it in 50 years or 75 years. But the problem is in 75 years, the world looks a lot different, and the question might also look a lot different. So personally, I worry a lot more about the climate, which seems to be a more imminent thing to worry about. And I would say that the chances of an AI that will exterminate us are actually smaller than the chances that AI will save us from Climageddon. Okay, so if you think about it that way, maybe it's a good thing that we're developing AI. Right, so the summary of all, whether you like it or not, AI is going to be part of everybody's life all the time, right? And it's going to bring a lot of good stuff. It's going to make your life more comfortable, safer, healthier, more efficient, if that's important to you. And but there's going to be challenges, right? There's going to be challenges, and we now have to deal with these challenges. And the choices that we are making now will actually determine the society we live in tomorrow, right? And so I would say, do not worry about Terminators like Hawking does. I would say, worry about your privacy. Where does your data go? Or worry about AI systems that discriminate, right? or worry about, you know, systems that can manipulate you, or your political choice, or, you know, social credit system that sort of starts to determine how you behave. And of course, you should worry about the climate. Thank you very much.